Homework Hotline, what is your emergency?
Here we are, it's the start of our homework show, and we want to help you with your homework questions.
So how can we do that? We're a live show, so you can call us and we can answer your questions in real time. And you can watch us on Comcast Channel 22, Prism TV, Channel 8007, YouTube Live at Denver DPS TV, Facebook Live at EG Homework, or live stream at livestream.com, and you search for DPS TV 22.
Yeah, and when you give us a call, we can help work through the problem that you have with you, kind of answering more of your questions in real time. You can give us a call at the number on the screen. Let's see if I'm pointing the right way. All right. 720-424-1666. We're here on Tuesdays and Wednesdays from 4:30 to 5:30 p.m. Anyone want to tell the audience what kind of questions we can answer?
I'll take that. So we answer questions on pop culture. Just kidding. Though we could probably do that for you, Becca, right? Very pop culturally knowledgeable,
No,
right?
not at all.
She's the go-to for pop culture.
Not at all.
Pop culture questions, and then while we're at it, we can help you with some other stuff. So I will actually be able to help you with your science questions. I'm a science teacher over at the Contemporary Learning Academy, and my name is Sam. Next to me here are Nathan and Becca. They both teach math at Emily Griffith High School, and they can help you with your math questions.
And both of our schools sponsor the show.
So today we also have a science demonstration. Sam leads us through the demos. You can do most of them at home with adult supervision if you want.
Sam, I hear our demo is rather moving today.
You could definitely say that, and I'll be showing you some plantastic stuff a bit later in the show.
For those of you who want to turn in your questions through social media, we hear you. We have Casey here taking your questions through social media. Casey, tell us a little bit about yourself.
Hi, my name is Casey Orr. I'm actually an intern here. I'm a student at the Art Institute of Colorado, and I'm here to answer your questions via social media today. We have you on Twitter, Gmail, and we also have you on Facebook, however you want to enter your questions. I'm also the trivia master for today. I'll have a trivia question we'll say at the top of the show, and by the time the show's over, we'll be looking to see if any of you have chimed in with your answer. If you answer the question correctly, you will win a prize.
All right, so what is today's trivia question, Casey?
Today's trivia question is, what is the strongest known magnet in the universe?
Oh, I feel like this could be tricky.
Love is definitely the answer to that question, right?
Easy. All I can picture is one of those
That's a freebie.
giant magnets that move cars at the
Oh yeah, those also
junkyards.
are strong.
Yeah, probably not the strongest.
I was thinking something like that, but then I don't know.
Probably not, but that's just all
Probably
I'm visualizing.
not.
Or one of those giant cartoon magnets from like Wile E. Coyote or something.
That was my next thought.
Yeah,
How'd you know?
Acme makes the best.
We're just giving you all kinds of ideas here, so
Yeah,
call
those are
something
all
in.
good guesses.
So if you do guess correctly or know the answer, definitely give us a call. You could win 2 symphony tickets to a symphony of your choice. You could also, if you wanted to, send in your question or the answer to the question on social media. So let's give you all that information right now. So you can call us, as Nathan mentioned earlier, but you can also get in touch with us on social media on Facebook or Twitter, as Casey mentioned, at EG Homework. That's our handle. You could text your questions to us. The number is 970-680-3771. That's a little bit different than our phone number. But you could also email us your questions at homework@emilygriffith.edu. So all of those options to get your questions to us. So let's go back to Casey and start at the social media board and get some questions that have been waiting for us answered.
Excellent. We've had a couple here math questions ready to come up. And the first one is going to be, how would you graph the following equation? We have y equals x plus 3 squared plus 4.
Is the x plus 3
is in a parentheses, yes.
Plus 4. Okay. I can do this. This is actually what we're working on in my classes right
perfect.
now, so might as well. So if you check out my screen, this is the equation that was given to us. Now, I'm also going to try and put some grid paper up here, if I can do that. How do you do? Here we go. This is how we do some grid paper. That way I can actually graph and it can maybe look a little bit neater. But one of the first things that I guess there are a couple methods to doing this. One would be very simply an input-output table. Choosing some x values, plugging them into the equation, and then finding out the y values that go with it. That is always one way that you could graph a function. However, if you know a little bit more about this particular function, you can use those clues to make the graphing a little bit easier. So I'll explain that method to you. First off, this is a quadratic equation, meaning, it's to the variable is to the second power. And why that is significant is because it tells us the shape of the graph. Actually, the degree of any function, or highest exponent, is what tells you the shape of the graph. And so because this is a quadratic, or an x squared, it is always going to give us this U shape, which is called a parabola. So knowing the shape might help us graph this a little bit better. Also knowing a parabola, if you know anything about parabolas, you know the end behavior of our graphs, it either goes up, or both down. We also know that a key feature of a parabola is the vertex. And that is a very important point on a parabola. It's either the minimum or the maximum. Now this particular equation is already in what's called vertex form. Quadratic equations can come in a bunch of different forms, but when it's in vertex form, you can actually see what the vertex is. And vertex form, I'll kind of write this on the side here, looks like this. And the vertex, okay, there we go. And the vertex is always at the coordinate hk. So hk, meaning the h is your x coordinate and the k is your y coordinate. So this particular parabola, I'm going to get myself a graph that's not too gross. Try to go as neat as I can. So this particular parabola has a vertex. We can look at these two spots here, hk. Now one thing to note is that if you look over here, there's a minus in front of the h. So that means we need to do the opposite of what we're seeing there. So our coordinate of our vertex is actually going to be at -3. That'll be our x coordinate of our vertex. And then the y coordinate of the vertex is going to be at 4. So we're going to go to the left 3 and up 4. 1, 2, 3, 4. So that's where our vertex is of our parabola. I'm actually going to do this. I'm going to move this down just a little bit so that I have a little bit more space to move my x-axis down. So if I did that, my point's going to move a little bit. It'll be over 3, up 4. So here's our vertex. So from there, the other thing to know, and this would be another clue with graphing this, is this A. In our case, there's nothing written there, so that means it's a 1. This A tells us about a stretch or a compression in our parabola. And because our A is 1, our A coefficient is 1, that just means that there is no stretch or compression in our parabola. So if we were thinking of just the most basic quadratic equation like this, y equals x squared, and I'll do this, actually I'll do it in a different color so that we can differentiate. Here's what I wanted. All right, I'll do this one in green. So if I were to graph the most basic parabola, I have the points at 1, 1, and then 2, 4, just like this, over 2. So the shape would look like this. And my parabola is just shifted to the left 3 and up 4. So I can make points in relation to the vertex just like this one. So to the left 1, up 1, like this. Left 1, up 1, like this. And then left 2, up 4, like that. Left 2, up 4, like that. And I'm running into my coordinate here. So I will erase it. But that is what our parabola is going to look like. And that, again, is because our A coefficient tells us that there's no stretch or compression. Now, this is not the only method to graphing equations or graphing quadratics. This is just one thing, but it's using pieces of information that we know about quadratics to help us put that onto a graph. So hopefully that helps. If you do want another method or you're interested in knowing another method, let me know. Would you say anything differently, Nathan? Would you?
No, I sometimes recommend if students just don't remember those shifts to just like do what you mentioned, the input-output method, but they typically find out pretty quick. That's a very tedious way to do it.
It is so tedious,
especially it's hard to find where that vertex is if you're just like guessing numbers. You got to find where that symmetry is. So
yes.
I think really understanding that relationship and seeing how that shift happens and how it affects helps a lot. I think that's a really good way to do it.
Also, where you were saying with that method, if you go back to my screen real quick, I'll show you another shortcut really quick that might help. If you were to know where the vertex is, as you mentioned, then you could maybe do input-output with the points that are around it. So I know my vertex is at -3, the x value of -3. So I might plug in -2 and -4 and maybe some more points around it to find out where my y coordinates are.
Yeah, and
so then it might not be as tedious if you do it that way.
And actually bringing that up, this is called vertex form, right? So because it's really easy to spot the vertex. Sometimes you have them in standard form, and this can be written in standard form. And like you mentioned, finding the vertex, there is another method for doing that, right? We won't get into it, but there are different ways to graph these types of functions that have the same relationships and the same meaning, but are maybe in a different form. And that's why your math teachers, they're not just trying to torture you, but there are easier ways to do all these things. And it's generally one way that will always work, but might take you 25 minutes.
A long time, right. So we like shortcuts in math, too. So
they're efficient.
We tend to do those. All right. Well, thank you for the input. I do appreciate that. And let's go back to Casey, get more questions.
Awesome, guys. The next question is going to be for Sam. It's a science question, and much like our special guest today, it's also green. Our guest asked, why is converting salt water to fresh water bad for the environment?
Okay, so converting saltwater to freshwater is actually not inherently bad for the environment, but there are lots of reasons why doing it on a large scale can be. So the process of converting saltwater to freshwater is called desalination, the process of taking salt out of something. And at first glance you might think, okay, I learned that the Earth is, upper 70% water, or the surface of the Earth, that is. There's a lot of ocean water available to us. Why wouldn't we try to make drinking water and other kinds of water out of ocean water? And the process itself is fairly simple. It typically just involves taking salt water and heating it and allowing water, pure water, to evaporate off of that saltwater liquid, and then catching that saltwater or that freshwater vapor and condensing it in another area. And there's actually ways that you can do this that are totally energy efficient. They might not produce a lot of water, but if we jump to my screen, one way that you can do desalination is through what's called building a solar still. And this is in French, apparently. I'm just realizing. But that's fine. It basically describes what you can do. You can set up just a hole in the ground, put a cup of water, cover it in plastic, and the heat of the sun will actually heat water out of the earth. It'll evaporate and it'll collect inside that cup. So you could also do this with salt water in a lot of different ways. That would be a way that you could do it without causing any kind of environmental damage at all. But it would be hard to do that on a large scale. So I'll just show another picture to sort of make the point of why this is bad for the environment. This is a diagram of a desalination plant, a large-scale desalination plant. And these do exist. There are times or locations and times where it has made sense to desalinate water. And the process of doing that on a large scale means building a big factory that can heat large amounts of water. You can see, I'm not going to go through this diagram, but it's a complex plant that's going to run a bunch of water through it, heat it up, collect the steam of that water, and then dispose of the salt or the remaining brine water. And that takes a lot of energy. And so the reason that desalination is often said to be bad for the environment is because you have to power a plant like this using electricity. And most electricity is still today produced using fossil fuels. I'll just show really quickly energy consumption in the United States by source. So this is in 2015. We can assume that it's probably close to the same today. You can see that most energy consumption is still petroleum, natural gas, and coal. Right? So those are fossil fuel sources. Those produce a lot of the electricity that we have in the United States. You can see that there are small amounts of wind and hydropower and solar power being produced, and all of those sources are definitely growing as time goes along. But for now, as long as we're doing environmental damage to create energy, desalination on a large scale will always be bad for the environment.
Awesome.
So it's not actually doing it, it's the cost of doing it.
Yeah, it's really the cost of doing it. I mean, taking water out of salt water, and if you'd be left with salt and water, you could sell the salt as table salt or salt for streets. You could do, I mean, there's no problem with that at all. And actually, that'd be great if we could do it. If we had an unlimited free energy source, we would desalinate water and it would be great. And people would stop complaining about a lack of fresh water, but we're not at that place.
Do you know, I had heard this recently, and only really briefly, because there's a lot of concern about, like, we're going to run out of water. Mm-hmm. We're going to run out of fresh water, and because there's too many people, we're drinking all of it and using it, whatever. And there's, all these, like, concerns, especially with California always having droughts and issues there. Mm-hmm. But then I read something that said, like, it's obviously not possible, right? Not possible. The water gets recirculated.
Right.
So the risk is really just having a deficit and not enough people. So not enough water for people.
Right. The risk is removing fresh water from locations where it's needed.
Right.
You think about aquifers in California. Look up sometime the amount of produce that comes from California, from the Central Valley of
and
California.
Bottled water.
And bottled water. There's an aquifer underneath California that is being drained. It's a serious, serious issue. There's plenty of fresh water. There will continue to be floods. Once the water goes out to the ocean, evaporation brings it right back to the mountains. And it's a process that will repeat forever. But if it doesn't rain in the same place it's been raining for millennia, and you stop getting recharge of an aquifer, which is what we're seeing in California, you really run the risk of, it's not that there's not enough fresh water in the world, there's just not enough fresh water where there used to be, where a lot of people depend on it. So I think that sometimes we oversimplify when we talk about environmental issues. They can be complex, and you have to sort of pick them apart. But we are in danger of running out of fresh water in a sense, because we're running out of it in certain locations.
Interesting.
That does make a lot of sense, though.
Yeah.
All right, Casey.
All right, our next question, it's going to be a word problem question for Nate and Becca.
All right.
Whenever you're ready, I'm going to read through it. Okay. Mario walks his dog in the park once every 8 days. Aiden walks his dog in the park once every 14 days. Today, both Mario and Aiden walk their dogs in the park. How many days will it be before the boys both walk their dogs in the park on the same day?
So I'm thinking about this problem already, and I'm trying to think of an algebraic way of doing it, and I'm wondering if it's more just like a least common denominator.
Multiple.
Yeah, least common multiple kind of problem, right? Like,
yep.
I was like, I automatically always want to be like, let's write an equation,
set up an
right?
equation, yeah.
But we'll talk about that. And you're really good at explaining this, so please feel free to jump in.
Sure.
And, like, if I'm throwing some terms out there. Okay, so what are the names again? Mario and
Aiden.
Mario, and Aiden, A-D-A-N?
I have A-I-D-A-N, but I'm sure.
Okay, I don't want to spell Aiden's name wrong. Right. He might get offended.
Aiden might get mad.
So Mario is every 14 days?
Mm-hmm. Okay. Poor dog.
Yeah, I know. Dog must be.
Yeah, geez.
Unless
Get your
the
dog
dog's
out more
like
often,
my dog,
Mario.
and after 14 days, take her for a walk, she's good for another 2 weeks. She's exhausted.
Yeah.
So, okay, Aiden every 8 days. So this is actually a matter of like we had just kind of briefly talked about, it's a least common multiple problem. We want to see where these kind of numbers are going to match up again. So I'm trying to think of how I would explain it without actually just doing it. We could think
you could say like day 1.
Okay, so day 1, they
are
both walk their
walking it
dogs.
together.
So day 14, Mario's going to walk his dog again, right? And then he's going to wait another 14 days. The dog's going to be a little crazy, so he's going to take the dog for a walk again. And another 28 days. And I'm just going to do this a few, right? And then another 14 days. So we say least common multiple. LCM is how it's usually abbreviated. Meaning like what we're doing is we're saying if it's every 14 days, we have multiples that are in 14-day increments. So 14, 28, 42, we're just adding 14 days each time, because that's when this poor dog is getting a walk. Now, Aiden's every 8 days. He's a little bit better. That's still not great. But he walks his dog at day 8. And again, every time he walks his dog, that's a multiple of 8. So 8, 16, 24, 32. And all we're doing is adding 8 days in between every time he walks his dog. And then we get to, we'll just keep on going, 40, 48, 56. And we notice here they still have not walked their dog together, right? So we're going to keep going with Mario. I can never see my pen. So we're at 56. It's 14. Wait, did I mess up somewhere?
No.
No, that's right.
There it is.
70, 84. And what you could be thinking about here is, aren't any of these days... Oh, we already passed it. Okay. So one way, I wasn't paying attention. I was just adding numbers, right? I got a little lost in that. You were
But
like,
it's
that's
easy
it.
to
And I'm
get
like, what are you
lost in
talking
it.
about? 70 is not right. That's what I was thinking. So one of the ways you could also do this, instead of doing this for both of them, is think, okay, Mario's walking his dog every 14 days, and we can just write out a list and keep going with the multiples there. And if you're really good at your factors and like your times tables, you could actually say, well, which one of these numbers for Mario is 8 a factor of? And we can say, okay, 14, 8's not a factor. 28, 8 is not a factor. And when I say is not a factor, we could test that and we could say, is 14 divisible by 8? No, we're going to get 1 point something. Is 28 divisible by 8? No, we're going to get some decimal. And we can keep going and say, like, okay, this is also not, 8's not a factor. But then when we get here, and if you're paying attention, not like me, you could say 56 is divisible by 8. So, and again, to show you that, 56 divided by 8 is 7. So that means that 8 is a factor. So after 56 days, they will finally walk their dogs together again.
Yep.
Do you have anything to add to that?
No,
Okay.
no, you did a great job.
Thank you.
Yep, nice vocabulary too.
Yeah.
Good job.
I try.
All right,
You guys ready for the
back
next
to
one?
Casey.
Excellent. Okay, the next one's going to be back to Sam, and it's another green kind of question.
All right.
Says, we are learning about different kinds of plants and animals and how they are classified. I was wondering, is mold a kind of plant?
No, it is not a kind of plant. So, let's see. So mold is actually a fungus, or molds are fungi. And I just want to explain a little bit about what that means, and then we'll think a little bit about, this is mold on bread, is that right? Or is mold?
Mold,
Mold.
it could, I think, on
Well,
bread
no,
or
no.
wherever.
We'll talk about mold.
The subject says what's green and grows on old sandwiches.
Okay, cool. Well, give me just a second here. Okay, we could jump to my screen, please. Okay, so it is tempting because molds are funguses like mushrooms are funguses, and maybe mushrooms are they're a fungus that we think about more frequently, maybe because we eat them, possibly. They're more visible to us. And mushrooms look a little bit like weird plants. I mean, they have stalks and kind of top parts, and even some mushrooms have what you could call flowers in some sense. So it's tempting, and I think a lot of people just sort of assume, maybe I don't want to speak about what other people know, but it seems like some people think that mushrooms are plants. And indeed, mold also kind of looks like a planty type thing. It can often be green like plants. Some mold, I think, can be photosynthetic like plants. So it makes sense that people would make that mistake. But actually, funguses, we're as closely related to a fungus as we are to a plant. And a mold is as closely related to a plant as it is to us. So this picture that I have on my screen is the phylogenetic tree of life. It's a phylogenetic, tree of life. We use this to sort of describe how we classify life, how we divide life up into different groups based on their characteristics. So here at the bottom of this tree of life, this branch is all of life in one single trunk, I guess. And then the trunk splits into three major branches: bacteria, archaea, and eukaryota. And so these are all domains. There are three major domains. And animals, fungi, and plants, the three I was just talking about, the three that we think about most because we're animals and plants are all around us and we eat fungi and fungi grows on our bread. We think about animals and fungi and plants as being like most of the life on Earth. Some of us might be aware that there's a lot of bacteria, but we never really, in just average talking between people, talk about archaea or even recognize the fact that even within eukaryota, which is the domain that we belong to, there are many other kingdoms, like the animal kingdom, the fungi kingdom, and the plant kingdom. You can see the slime mold kingdom, the ciliates kingdom, the flagellates kingdom. So there's a lot of life out there, is the point that I guess I'm trying to make. Mold itself belongs to the kingdom fungi, just like mushrooms belong to the kingdom fungi. But then even within that kingdom, there's so much diversity. Imagine all of the different kinds of animals that there are on the Earth. There are that many different types of fungi. Imagine all of the different plants that there are on the Earth. There are that many types of fungi. And there are many, many types also, flagellates, ciliates, other types of eukaryotes, not to mention the other domains. So, anyways, mold is a fungi, is the answer to that question. It's not a plant.
I've always thought of myself as a fungi too.
Nice.
Not a plant? You're not a plant?
Not a plant? Not a plant guy? Fungi?
All right. Well, we're going to take a little bit of a break. And speaking of plants, we will, when we come back, we will be doing our science experiment. So we'll see you soon.
Okay.
Lindsay Gore
Now I'm ready.
preps for another client.
It's pretty crazy in here. We do a lot of business. All wrapped up. Uh-huh.
This full-service salon is Strand's Hair Studio.
I do own Strands. I bought it 2 years ago. I worked here for 9 years almost before I bought it. In the back of my mind, I always knew I would like owning my own salon, and I love it. I know.
It takes a lot to run a business.
Oh, really?
Choosing the right school makes a difference.
After I started at Emily Griffith, I had a cousin in cosmetology school at another place. We would kind of trade stories, and I became very grateful about where I was learning. I felt like I was exposed to a lot more real-life situations.
The cosmetology program teaches the business side of hair.
To me, that's of higher value than learning how to do hair, because you learn how to do hair by doing hair. And so you really hone those skills when you're out of school, but knowing how to run your business is what's going to make you ultimately successful.
This business owner looks for stylists to hire, but often sees them unprepared.
I interview people for jobs here too that have gone to different schools. Some of them just come out woefully unprepared. You know, they can do a beautiful highlight and great haircuts, but they don't know how to organize their time. They don't know how to talk to people.
Lindsay talks to her clients.
And they have pieces of things that they've dug up.
Even small talk makes a difference.
Right, exactly.
More importantly, you need to listen.
Listen to your peers, listen to your instructors at school, and most importantly, listen to your clients. This industry changes constantly. You have to be open to listening and learning new things.
Take in this advice. You're not going to get rich quick.
You don't walk out making $20 an hour or $40 an hour. You spend your first year sitting around and hoping that you can get someone in your chair.
Understand, you have to put in the time.
Any career takes 4 years to be good and 10 years to be great.
And all this leads to a rewarding career and happy clients.
Making people feel pretty and making people leave happy. And that's a beautiful thing, and that makes me go home happy.
Okay, hey, so welcome back to the science lab. I guess this is really just my desk. We just moved over, but let you guys in on a little secret. So, guys, we're talking about movement in plants today. And I have a couple cool plants that move quickly that I'm really excited to tell you about. But those plants are sort of special. So the question I have for you guys is, average plants, normal plants, boring plants, not like the ones that I have, do they move?
Only when the wind blows them.
Only when the wind blows them, right,
Yeah.
of course.
Yeah. Well, they move.
Everyone
You
agree?
just can't really,
Growing, I guess,
see
is
it, right?
technically
Okay, so
Oh,
they
yeah,
grow.
slowly.
Isn't growing technically motion?
Yeah.
Okay, fair enough. And what did you say, Becca? I'm sorry, I missed it.
It's pretty much the same thing, that they do move, but it's just so slow that you can't witness it.
And I think that's the big thing, right? We don't notice that plants are moving because it happens so slowly typically, although we're going to be able to show quicker movement today, which I'm excited about. But in general, there are two kinds of movement in plants. And if we could jump to my screen at this point, there are two types, and you can just leave it on that one. So there's tropic movement and nastic movement. And that probably sounds technical and complicated, but it's actually fairly simple. So tropic movement is movement where the direction of some stimulus causes the direction of movement in the plant. For example, gravity, plants and seeds can actually sense gravity. And it's that sense of gravity that allows roots to grow downward and stems to grow upward. So that's called gravitropism. The force of gravity pulling down means that the root is going to be positively gravitropic because it's going to move in the direction of gravity, and the stem is going to be negatively gravitropic because it's going to move against gravity. But plants have that sense inside of them.
So I have a question.
Please.
Because I'm looking at this image up here, and I had a tree growing up in our yard that was kind of grown out at an angle
Yeah.
and then up.
Yeah.
And it was because there were bigger trees around it, so it grew towards the sun. Would that be tropic movement?
Yeah, it's exactly tropic
Okay.
movement, right?
Okay.
So that's why we get plants moving toward certain stimuli. So another major one is light. There's phototropism. Okay. There's phototropism. So that's going to be plants moving toward the light.
Sunflowers.
Sunflowers, right? So so sunflowers are a great name because they're flowers that have something to do with the sun. But I feel like people get confused because they just look like suns.
No, it's because
and so they think,
face the
right.
sun.
That's what I thought.
That's why I love
Yeah.
them.
So in Spanish, the word for sunflower is mirasol, which means looks at the sun. I think that's such a great name because that's what they do. If you watch time-lapse videos of sunflower fields, you can see the sunflowers following the sun across the sky during the day. It's really pretty cool.
Like an incredibly slow tennis match.
Right, it's like a super slow tennis match where the ball like just keeps going around and around. Okay, so first question for you guys, or first demo with the plants. The plant furthest from me right now is my Spanish olive tree that I'm growing. He's tiny, but he's doing good. His name is Ferdinand. I name a lot of my plants.
Hey, Ferdinand.
But could you guys tell, Ferdinand has had some phototropic movements. Could you tell what direction, or what side of Ferdinand faces my windows in my classroom?
This side.
Yeah, I want to say this one.
Yeah,
they're all kind of
Why do you
the
guys think that?
leaves are
The leaves
The
are
leaves,
larger
yeah.
that way.
Right, and you
reaching
can even
out,
see,
yeah.
right, even the leaves at the back, you'll notice
They're
are
kind of
tilted
facing, they're like,
toward that
"Wah."
direction, right? So you guys are exactly right.
They're missing
And I
out,
guess I
and
made
they're
it easy
smaller,
by
too.
pointing it forward, but
Oh, yeah, they are smaller.
and you can see, so let's just rotate this guy here. Actually, Becca, do you mind just turning him around? You can see, now you guys are sort of facing all of the front sides of the leaf, the part that's going to catch all that light and perform
This is the
photosynthesis,
way.
right? And the backside, right, is the backsides of leaves. Phototropic movement. Oh, you guys get a good shot there? Yeah. Look at that. That's the backside, right? So that's the side that faces my classroom. So that's the side that we see, and then it's facing outwards. And all of my plants do this, and sometimes I'll even turn them around, after a couple months, just to get them to grow back the other way, right? Okay, so there's tropic movement, which is moving in the direction or against the direction of a stimulus. But then there's nastic movement. Nastic movement is movement that happens, it's related to a stimulus, but it is not, the direction has nothing to do with the stimulus. Can we go to the next slide really quick on my thing there? Okay, if we could jump to my screen. So this is just an example of phototropism, the plant growing toward the light, toward the stimulus. Go ahead and go to the next one. Gravitropism, right? Stems grow away from gravity. Roots grow toward the pull of gravity. Okay, next one. And then you can do things like Nate was sort of talking about, right? You can put plants in weird orientations, and they will, they'll continue to grow, stem upward, root downward, right? That's why you can plant a seed, and you don't have to worry about putting a certain side of the seed up. This seed knows which way to grow. And people even get their plants to do really strange things by moving them around as they grow. Or Nate's backyard tree just happened naturally, but same deal. All right, next one. So phototropism happens, and it's kind of cool how this happens. There's a molecule that moves away from the light in a plant, and it makes the other side of the plant stretch out, and that's what tilts the plant toward the sun. So I don't know how well this diagram sort of shows that, but those little pink dots in there are supposed to represent auxin is the name of the molecule, and it moves away from light, again, stretching out one side of the plant and causing it to bend over. Okay, next slide there. The other really big thing here is called turgor pressure. That's sort of the amount of fluid inside of the plant. Have you guys ever had a house plant and not watered it for a little while?
All the time.
Oh, that's, yeah.
So what happens? So before it
guilty.
dies, before you kill
wilts.
it wilts, right? And what does wilting mean?
Dying.
Well, okay, so wilting
It's like
doesn't mean
shriveling up.
shriveling, and it also gets kind of like,
Yeah.
right? And that's because the turgor pressure in the plant has gone down. There's not a lot of fluid holding the plant rigid. So if you were to water, and I have a strawberry plant in my classroom, and it needs a lot of water, and over the weekends a lot, I come in on Monday and it's like, and if I just give it water within about an hour, it's back to being upright because the turgor pressure's increased.
It's kind of like when a balloon animal, if you've had it for a couple of days, it starts to drip because the air pressure inside.
Exactly.
So you want to get more stuff
You
in
can
there.
get more air in there, in this case, fluid.
Fluid, yeah.
So, exactly. Turgor pressure also allows plants to move in these kinds of ways. A plant can self-regulate how much fluid goes to a cell to bend or stretch cells. Does that make sense?
Mm-hmm.
Yeah.
So I really want to show you guys this plant here. This is called Mimosa pudica, or the sensitive plant, or shy grass, some people call it. Okay, and it's already a little bit closed up. But I'm still going to have each of you guys touch it, and we'll see some Nastic movement, what's called Monastic movement, because it's caused by vibration. So Nate, can you go ahead and just knock one of the, just with your finger, sort of knock one of the ends of the stems?
Oh, it's closing.
Did you see some? Do you want maybe that's maybe?
the other side.
This
In
one.
the
Can I do
camera.
it? Can I
Yeah,
do
please,
it?
please, Becca, you do that one. Okay, we should get maybe a little bit. Okay.
Oh.
Yeah, that one works. So actually knock, go ahead and knock the stem because, okay, so normally it would be open. Go ahead, Becca. Do that.
Like
Do
it's
that one
great.
right there.
This one.
Oh, it looks so sad.
I'm so sorry.
And it does feel like you're sort of hurting it, right?
It's a sensitive plant. You're being a bully.
Yeah.
Right? And, okay, so really gently. Really gently. Hold on. Really gently. I want you to, am I getting in the way? I want you to kind of put your whole hand into it, okay?
Okay.
Go ahead. Gently. Keep going. Okay, now pull away. We're getting a lot of, so in a way, I think it is already kind of closed up a little bit on us.
It just saw us.
And really a lot of the closing, so normally the leaves are totally open, and I brought it downstairs, and it was really just the vibrations of me walking it downstairs did this.
Yeah.
And it opened up a little bit. Oh, Becca got some good movement there. See if you can get that one to go down.
Which
that
one?
stem right there.
The stem?
Uh-huh. Okay. Sometimes it's more responsive than
What
other
about
times.
this guy?
Pull it down.
Oh, is it a little bit open? In any case, this is
I'm so
seismonastic
sorry.
movement that these guys are playing with. And you can see that little bend right there. But this is vibration causing movement. Now, the movement has nothing to do with the direction of the vibration, but it just knows to move. And it's actually not totally understood why, it's not totally understood why this plant has this movement. It's believed possibly to be a defense against bugs that eat leaves. So when a bug would land on there, the leaves would close up and the bug would get scared and jump away. So that could have been one of the reasons. There's also this other kind of Nastic movement called Nastic Movement. It sounds so crazy. Nastic. Sounds like, I don't even know what. But Nasty or Nastic movement is when plants close up at night and then reopen in the day. Maybe you guys have seen this, but flowers, right?
I had a Brazilian rain tree, a little bonsai tree.
Absolutely.
And it would close up at night, and then during the day it would always go
open back
quite a
up,
bit.
right? And they're doing that for different reasons, but typically that is also to conserve water. So as a plant closes in on itself and decreases its surface area, it can hold water better. Water won't evaporate away from it. So think about it. During the day, when a plant's getting light, it wants to use that light to create sugar through photosynthesis. But at night, it would prefer not to waste energy, so it kind of shuts down. So you get these Nastic movements, and if you do a time-lapse video of a plant, you always see this kind of movement up and down or toward the sun backwards over the course of time. It's just that we can't notice it immediately. Okay, quickly before we end here, I just want to draw our attention to my little guy here. It's a, well, what is it?
It's a Venus flytrap.
Yeah, it's like one of the most classic plants ever, right? Everybody knows what it is. I've got this guy growing upstairs. There's a few flies in my classroom, so I'm seeing if, he'll take care of them. This guy is really small and will grow I think with time, although they're a little bit tricky, and I don't want to have us actually stick our finger in it, not because it's dangerous, but just because it can actually hurt the plant.
I've seen Little Shop of Horrors. I know it can be a problem.
Yeah,
It can
stay
be
away.
dangerous.
Be careful.
depending on
Be careful,
the
right? But this is also Nastic Movement, and related. It's Monastic Movement again from a bug landing on it and shaking it up a little bit.
So I had one of these too when I was a kid,
Oh,
and
nice.
I would try to stick flies in it, but it would never.
Yeah.
It was too slow, and so I was told to put little drops of beef blood
Really?
into it
That's so
for
interesting.
nutrients. I don't know if it worked.
I wonder if that
but I
would
did
work.
I don't know. I'll go grab some jerky.
Yeah.
I was wondering why these plants developed to where they would eat meat rather than just use nutrients like other plants.
That's a great question, right? So some form of sustenance. So imagine soil that's depleted of some kind of nutrient that plants would need. So for a long period of time, it just goes unused. There's just soil without plants on it. That soil is valuable real estate, in a sense, for any kind of living creature. At some point, there would already be bacteria and other things living on it. But at some point, through random mutations, a plant would evolve to be able to live in a situation like that because it would be getting, and I would imagine it would be some kind of a nitrogen-based compound from bugs, from insects. And so how that actually started, I can't say, but ultimately it would be probably because you would want to use some sort of land that's not providing a particular resource, and you're making up for it by eating insects. And Venus flytraps, though the most famous, are by no means the only bug-eating, insect-eating plants.
Is there anything in them that makes a fly attracted to them?
Yes, they release, I want to say pheromones, but I could be incorrect here, but plant pheromones. They release an odor that flies are attracted to, or other insects.
Awesome.
Yeah. Any other questions, guys?
Oh, goodness. How long does it take to, like if a fly, like just a regular sized housefly flew in there, how long would it take them to actually digest that to where the fly?
It takes a long period. So this one right here is, I don't know if you can see, but those are mosquito legs sticking out of the other one. It's actually got
for you,
a
plant.
mosquito in
Yeah.
there. And
Thank
it'll
you.
be, at least 48 hours before that thing opens back up. But I think that the time frame can range based on how large the bug is.
Thickness of exoskeleton and stuff like that.
Right, that kind of a thing. There's a little tiny spider that's kind of made a home in between two of them there. I don't know if you can see it. It's so tiny. But yeah, it's like kind of great real estate because flies are going to come down there and maybe
very
get caught.
risky.
On the other hand, if you wander a little too far, but he's so tiny, I feel like they would be able to eat him pretty quickly. Essentially, they secrete a chemical that then dissolves the body, and then they're able to absorb nutrients in that way.
So when you say like we don't want to poke it and make it close because it's going to hurt the plant, is it hurting the plant because it's kind of like closing for a while and missing opportunities, or is it hurting?
Could
it
be that, but
because-
also we just don't want to.
Touch it.
I wouldn't want to do it with our fingers because we could leave oil residue. We could do it with sort of a sterile tipped
okay.
something, but I just don't want to bug him. He's tiny and
Bug in.
Yeah.
you know,
good pun.
bug him.
game.
Nice. I didn't even notice I did that. All right. Well, on that lovely note, I think we'll wrap it up. So thank you guys so much for joining us here. Plants are super cool. You should get some, but talk to your parents first. We'll see you back in the Homework Hotline studio in a few minutes.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when why, or how.
Because now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
Welcome back. Hopefully you enjoyed our science experiment, or I guess demo, on plants that move. I definitely did. I was so interested in that. That was really cool.
Yeah, it's cool stuff.
I had no idea that existed.
Yeah.
No idea. What we do here mostly is answer homework questions. So if you still have homework questions, I'd like to give you our contact information in case you're just joining us. You can get a hold of us, number on top of your screen. That's the best way to get a hold of us. But there are also some other ways to send in your questions, and via social media, Facebook and Twitter at EG Homework. You could text us, 970-680-3771. Or email in your questions at homework@emilygriffith.edu. So get your questions answered by the experts. I called us experts. All right, Casey, do we have any questions waiting for us?
We do have some more questions, and funny enough, we actually have a lot more of these green kind of questions that kind of go along with our plants. This is going to be a math question, actually. Looks like it's about area concerning planting a field. The question says if you need 1 gram of grass seed to plant 1 square meter of grass, how much grass seed would be needed to plant an entire soccer field that is 110 meters long and 70 meters wide?
All right, I'll take that one. So that's really just an area question. Mm-hmm. So when we talk about, let me get those dimensions again really quick. It's 110 meters long and 70 meters wide.
Mm-hmm. That's right.
Okay, so we'll imagine that this is our soccer field, 110 meters long and 70 meters wide. So if we imagine that 1 gram of this plant seed will grow 1 square meter, again, this becomes an area question. If we think about like this, it'd be 1 square meter maybe. It's obviously not to scale because you would need 110 of them there. So when we say 1 square meter, we're saying that this is 1 meter by 1 meter, and we just drop, a gram of plant seed in there, and then, like we just talked about, it grows to beautiful grass, and we can mow it and stuff. It's pretty nice, right?
Yeah, it is nice.
All right. So now we need to plant enough to grow and cover this entire soccer field, right? If you ever played soccer on like a dirt field, it's not pleasant when it's fall.
Especially when it gets muddy.
Yeah. So we could imagine that this is like a bunch of these little squares, right? Like if I plant 1 gram of this seed, then I'm going to get grass to grow right here, right? And this is 1 meter by 110 meters by 70 meters. So what we need, and I'm not going to draw all of them because we would be here for a while, is we need that to cover 110. So if you could imagine, right, that we did this 110 times, and obviously not to scale, but we needed to do 110 times across, and we needed 70 times up, right? Because each one of these is 1 by 1. So this just comes down to our area. If we have 110, we can think of this as grouping, 110 groups of 70 going one direction, or we could say, so we have 110 groups of 107 or of 70, so we could multiply that, or we could say we have 70 groups of 110. Well, we end up with what? 7,700, right? And if I did it the other way, we still end up with 7,700. So like we said, this is really just an area problem, but what we're doing is when we do area, we're doing length times width equals the area. And in this case, what we're doing is we're saying we have these kind of groupings. So that would just be, if you want to call that 110 times 70, we would need 7,700 grams of seat in order to cover this entire soccer field?
I like how you explain that, because a lot of times with area, every student just says, oh, just take the sides and times them.
Without really understanding like what we're doing. And I always try to break this down in my geometry class to like, sometimes I get annoyed. They're like, I already know the area formula, but like try to break it down into these like little tiny unit, one by one unit measurements. Yeah.
And groups of means multiplication.
Yep.
All right, so we also have a trivia question that we would like to share with you one more time, just because we don't have a winner yet.
We haven't had anyone yet, but there's still time in the show. The trivia question is, what is the strongest known magnet in the universe? It means not just on Earth, that's everywhere in the universe. You can you can call in to our show, of course. We also have our homework at emilygriffith.edu, as well as we're on Facebook and Twitter if you have an idea of the answer. Otherwise, we have another question if everyone's ready.
Yeah.
Ready.
Excellent. Or actually, this one's going to be for Sam again. And what do you know? It involves
More plans, yeah.
People must have known. You must have leaked who our
right.
special guests were going to be.
I mean, they heard that pun in the beginning. They figured it
right,
out.
and they're like, "Oh, I got one for you, Sam."
He must know his plants.
All right. Our writer in says, we learned that plants need sunlight, water, and soil to grow the best, but is one of these more important than the other two? Like if a plant got plenty of sunlight and soil but little water, or plenty of water and soil but less sun, which does a plant need most of all, and why?
Yeah, definitely. Okay, so this is another situation where I think maybe we've oversimplified what plants need. Plants need sunlight and water, no questions. They die without one of the. They don't need sunlight. They need some form of light that has red spectrum and blue spectrum light. So you can do that with a machine. But they need light and they need water. Soil isn't really necessary in the sense of like you don't need dirt, but every plant needs some kind of a growing medium. So, for example, bamboo is often grown in like marbles. You'll see, people will have sort of beautiful little, cups of marbles, and they'll just put water in it, and you can actually see the bamboo's roots grow right through that. Or you can imagine like mangrove forests where much of their root structure is just right in water, or orchids. People often have orchids growing on trees or on boards of wood, that they like hang the board of wood and an orchid will grow like out of the wood. So a growing medium is necessary, but it doesn't have to be soil. But this leaves out really key things that plants do need. So, one really key thing, two things that a plant needs. A plant needs carbon dioxide, and that's because plants make their own food in-house, and they do it through a process called photosynthesis. So I'm sure most of us are aware that plants photosynthesize, but we may not be aware what photosynthesis actually does. So photo just means light, and you might have heard me use the word earlier, phototropism. So that's growing, a plant growing in the direction of light. In this case, photosynthesis just means, synthesis means making something, so making something from light. And a plant will use water and carbon dioxide to make sugar. And it uses sunlight as the power for that. So it needs carbon dioxide, it needs water, and it needs an energy source, light in this case. Okay, so I guess I'll just leave it at that for now. Plants need sunlight and water. They just need a growing medium. We would add carbon dioxide to that list. We could say they need oxygen, but they technically produce it when they go through photosynthesis. So they sort of make their own oxygen also. So I think I can leave it at just light, water, CO2, growing medium. So 4 things.
Awesome. Excellent. All right, well then let's give you a break. We've got a math question lined up. This one looks like a pretty simple. Looks like we're having an issue with order of operations, probably trying to find something simple. We have, I don't know if you can see it, I'll just read it to you. 7 minus, and in parentheses, 9 times 4, and that minus 12.
Times 4, and parentheses, and you said minus 12?
Minus 12, all minus 12, yeah.
Okay. So we do have to simplify this, and when we simplify anything, We use the order of operations, and you may have heard of those, PEMDAS maybe, or please excuse my dear Aunt Sally. That's another way that we use to remember what the order of operations are. But either way, this is the master order of things in math. I explain to my students a lot of times that, when we're reading something in English, and I say English because other languages have a different order of things, but when we're reading something in English, we always read from left to right, and that's just the rule of how we read it. There are other languages that we might read from the bottom to the top, or from the right to the left. However, the rule is in English that we read left to right, and if we were to read it the opposite way or any way different than that, it wouldn't make any sense. So in math, our master order of things really is our order of operations. And this is how we need to, I guess, in a way, read our expression. Please excuse my dear Aunt Sally, or PEMDAS, what that stands for. P is standing for parentheses, meaning we want to, I can't put my S in there, there we go. We want to simplify anything inside of parentheses if at all possible. Exponents is the E. M stands for multiplication and division, and then A and S stand for addition and subtraction. So we're going to start with what's inside of our parentheses. We'll rewrite everything else. When we simplify what's inside of the parentheses, 9 times 4, we end up getting 36. And then we rewrite everything else. So we do minus 12. And then now at this point, we actually only have some subtraction. If you have subtraction or addition and subtraction only, we just go left to right. So we'll start with our 7 minus 36. We get negative 29. And then we'll do negative 29 minus 12. And we end up getting negative 41. Is my math okay there, Nathan?
Looks good to me.
Okay. All right. So order of operations helped us simplify that.
Let me ask you this. What if there were no parentheses? Would there be a different answer?
No, because multiplication still would come before addition and subtraction. Good question. Fascinating. So unneeded in that problem. All right, Casey, time for trivia answer.
Trivia answer. All right, we didn't have anyone come in as far as I was aware, but our question is, what is the strongest known magnet in the universe? And the answer, are you ready?
I'm ready.
A neutron star, apparently. A neutron star is a super dense celestial body, which means out in space, that's made of mostly tightly packed neutrons. These are super dense things. They're typically only about 18 miles wide, which is really small when you go out in space. Most times things are a lot bigger, but it's got so much dense neutrons that it actually acts as a huge space magnet.
Sam, do you have anything to add to that? I feel like you could add
Yeah, let's give a little background. So I think, 18 miles doesn't sound small. 18 miles sounds big. Just saying 18 miles, bigger than us. But as a celestial body, that's like extremely tiny, like crazy tiny.
I mean, even like an island that's 18 miles wide is a small
island.
island.
Okay, right. Imagine an island that's 18 miles wide. You'd be like, this is a tiny island, right? Yeah. Imagine a neutron star. So the Earth, right? The Earth is a small celestial body. So what does that make a neutron star? Like an extremely tiny. And what it is that a neutron star is a collapsed larger star. You know, larger star, and at a certain size, stars will supernova, they'll explode and make a black hole. But at a smaller size, they'll collapse and form a neutron star. They'll tightly pack their magnetic field. The magnetic field gets amplified up to trillions of times. And
it's a lot of times.
It's contained in this little tiny 18 square mile area.
So magnetic is the force that, it's a magnetic force. So it's gravitational force?
It is a gravitational force that holds it together, but there was a magnetic field on that star before, and it collapses with, some of it gets broken off into space, some of it collapses with the neutron star and is amplified by the density of the star.
Gotcha. Okay. Always learning things on our show.
Yeah.
Always learning things on our show.
Look it up. Look it up online.
So we are going to have to say goodbye, but we will see you next week. Check us out on social media. We'll be back again next Tuesday from 4:30 to 5:30. Thank you for joining us today. We always appreciate your questions. And again, we'll see you next week.
Bye. Yeah, I was about to.